All right, let's dive into something fascinating, and honestly, a little scary. It's a paradox in materials science where a perfect finish might actually be a warning of total disaster.
I mean, think about it. It sounds completely backward, right? We pour so much effort, so much money into making parts that are absolutely flawless, perfectly smooth, incredibly hard. But what if that perfection, what if it's just a mask, hiding a deep internal flaw, a ticking time bomb that none of our best tools can even spot?
And this really gets to the heart of it. You've got this stark contrast. On one hand, you have the appearance, the promise of a flawless surface, extreme hardness, superior durability. But the reality, it's a whole different story. We're talking internal cracks, sudden failure, and a hidden weakness you'd never see coming. And let me be clear, this isn't some academic theory. This is a real and really dangerous problem.
So yeah, that's what we're digging into today. The perfect surface paradox.
And this is happening in some really critical places. Think aerospace, automotive, heavy industrial machinery. These are components that are engineered to take a beating, to be as strong as possible. And yet, they're failing. The scariest part, though, they fail without a single warning. There are no surface cracks, no visible wear and tear. Just, bam, sudden, complete collapse.
So you have to wonder, what's creating these surfaces that look so perfect but are hiding the secret? Well, let's take a look at the technology behind it. It's a process that basically gives steel its own suit of armor. It's a process called nitriding. And really, in simple terms, you're kind of baking nitrogen into the surface of a metal like steel. What this does is create this super hard, wear-resistant outer shell. They call it a case. And this case makes the part way, way better at handling fatigue and stress. I mean, this is a cornerstone of modern engineering for a reason.
So when you do this, you get these very distinct layers. See that outer layer? That's the super hard compound zone. Right underneath that is the diffusion zone. That's where the nitrogen is kind of soaked into the steel and made it stronger. Put them together and you've got this amazing protective shield over the softer core material inside. It's a really elegant solution on the surface.
But the real magic trick here, the secret sauce of nitriding, is something called compressive stress. The best way to think about it is like having a tightly coiled spring sitting just under the surface. This stress, which you can see in those shaded areas, is constantly pushing out. So when some external force tries to start a crack on the surface, this internal stress just pushes right back. It's an absolutely brilliant shield against surface damage.
But, and you knew there was a but coming. Here's the twist. That amazing shield, the very thing that's supposed to stop failure, it actually creates a brand new problem. And this one is way sneakier. It's a battle that happens beneath the surface.
See, here's the thing about stress. It doesn't just vanish. That nitrided layer is so strong, so good at its job, that it doesn't let cracks form on the surface. So what happens? All that stress has to go somewhere. It gets pushed deeper, inward, past that protective case, and into the softer, unprotected core of the material. So you haven't actually prevented the failure, you've just moved it.
This quote from the research just nails the irony of the whole situation. These subsurface failures are happening precisely because the nitriding process is so successful. Its own success at protecting the outside is what ends up exposing the weakness on the inside. It's wild. And once that fight moves inside, you're dealing with a whole new cast of characters, these hidden enemies. We're talking about all these different ways a failure can kick off deep inside the material. Things like fisheye cracking, starting from tiny impurities, or the layers literally peeling apart from each other. And that hardened armor on the surface? It's completely useless against threats like these. Okay, so look at this image. Up top, you see that beautiful, hard, perfect nitrated layer. Looks great, right? But the real action, the dangerous stuff, is happening below that. The main villain in this story is often what's called a fisheye crack. It starts deep down in the steel, totally invisible from the outside, and just grows silently. So what exactly is a fisheye crack? Well, it all starts with these tiny, microscopic impurities inside the steel itself. Little bits of non-metallic stuff left over from when the steel was made. And get this, a defect that's only 20 to 50 micrometers, that's smaller than the width of a human hair, can be the seed for a massive failure. That tiny flaw starts a crack that just grows and grows in that internal, almost vacuum-like environment, until the whole component just shatters out of nowhere. Okay, so this all leads to a really critical point. If the real danger is lurking inside, then our whole way of thinking about safety and inspection is, well, it's wrong. We have to start looking deeper than just the surface.
So when does this actually happen? You might think it's during some huge, high-stress event, but it's actually the opposite. This shift to internal failure tends to happen at lower stress levels, but over a really long time. We're talking hundreds of thousands, even millions of cycles. In those long-haul situations, surface cracking basically doesn't happen anymore. Almost every single failure starts from the inside out.
And folks, that right there, that is the massive, terrifying blind spot. All our standard inspection methods, even fancy AI monitoring systems, they're all programmed to look for flaws on the surface. They are completely 100% blind to a crack that's growing deep inside. So you have this perfect-looking part that gives everyone this false sense of security, right up until the second it explodes.
So, where does that leave us? It leaves us with a pretty profound question, doesn't it? If the surface can lie, if it can hide a fatal flaw, then what does strength even mean anymore? It seems like true strength isn't just about having a tough outer shell. It's got to be about the purity and integrity of the material, all the way down to its core. And that's a question that's going to force engineers to rethink everything.